So thanks, whoever's here. I know Friday night is not a great time, and some people are on midwinter break, or at least in the school districts around here, midwinter break, and I got some students. But yeah, I'm feeling a little sick today. I know I've been doing about short sessions for the office hours. I mean, obviously, just come by whenever I try to have them scheduled, and I'll try to be really more consistent. But yeah, if you have anything that you have any questions on, feel free to bring them by. I wanted, man, I had these interesting problems from my tutoring sessions that I kind of wanted to like bring up, but I didn't really do a good job prepping. So let me pull up some problems, and I'm curious. I'm just gonna do what I was planning on doing a couple weeks ago. Let me see if I can find it. I like this ball, not the angular momentum one, because a lot of you guys are doing like, let me see. I like this question. This is a cool question. This is a physics question. I've been doing some calculus, some everything, but yeah, there is that one. I'll work it out in a second, but I gotta take care of a few administrative stuff on my business side of things. So that's what I'll spend my time doing here. And as usual, please ask any questions. If you get stuck on anything or you're curious about anything about me, just feel free to ask. 10, 12. I'll do this problem in a second. But I thought I'd give, if anyone was around before, while I was taking care of some stuff, give you a chance to take a look at it, see if you want to try it. It's from an honors physics class, college honors level, so it's pretty hard. So let's look at this problem. All right, now I took care of a bunch of that stuff. I got one more thing to take care of, but I'll start with this problem. So I have two blocks with masses m and big M are free to move. The coefficient of static friction between the two blocks is mu s. So between the two blocks is mu s. Oh, they show it in the picture. The coefficient of kinetic friction between M and the surface is mu k. Calculate the minimum horizontal force required such that M does not slide down the side of M. Assume the blocks are accelerating rather than standing still. Okay. So I gotta do free body diagram for each of these. So I got little m here. It's got a force to the right F. Okay. The block must push back with a normal force. And I'm gonna say it's from M, big M. And this is little m. And then I must have a frictional force. It has gravity pulling down on it. And then I have a frictional force that's holding it up, right? No normal force, just frictional force holding it up. Okay, and the sum of these forces need to be 0. And then on big M, what are my forces? This is big M, so I have forces acting down, gravity, big M times G. I have the force from the block, which is going to equal to F big M here. I'm going to call it F little m. But it's equal and opposite. It has to be equal to this one over here. Okay. And then we have frictional force here. Now, we don't know that this force is equal to this one because it's accelerating. We're assuming accelerating to the right. So this force is definitely not equal to that force. So you can't assume that this is big F. You can just assume that it's equal to the force. Like, this is Newton's third law. The little block pushes on big M, and big M pushes on the little block, right? And then we have a normal force here. Okay, so let's do the net force equations. Now, I know the force of friction in the y direction has to equal little mg. That's mu s times the normal force. So we have to check out what the normal force is. The normal force in terms of this friction is the block pushing back up on it. So it's mu times Fm is big M is equal to mg, right? Okay, so that's the vertical direction. And then, that's the vertical direction, that those have to be equal. And then the horizontal direction, let's assume it's accelerating to the right. I have F minus F big M is equal to little m times A. All right. And my goal is to figure out what F is. So I'm going to solve my equation for F. It's F big M plus little m times A. I know this is really hard to tell, but this Fm, these two forces are equal. It doesn't really matter. Okay. So that's my equation so far. I could solve for Fm, right? Fm is going to be mg over mu static force. And I could plug that into there just to make it this. Mg over mu s plus ma. The problem is A is not, I know all of these values, or all of these values are presumably defined, just that I don't know what A is. So that's why I need to do the free body diagram for this one. Here, big mg is equal to the normal force, because it's not accelerating in the vertical direction. We're only accelerating in the horizontal direction. And then the horizontal direction, I would have F little m minus force of friction is equal to big M times A, right? But this friction, this little m is the same as this big M, because that's by Newton's third law. And the force of friction is going to be mu k times the normal force, because it's kinetic friction, because it's accelerating. Okay. So I can now, and then this normal force I know is big mg, so big Fm minus mu k capital Mg is equal to big M times A. And I can solve for A and then plug it into there. And then that goes into there. So I get the force here would have to be mg over mu static friction plus little m times Fm minus mu k mg over big M. Now this Fm we already found was mu g over, it's this quantity here, so that can go into there. So I get mg over mu s plus little m times mg over mu s minus mu k mg divided by big M. And I'll just split this into two fractions. So I'll get mg over mu s plus, dividing out the m, this would be little m times mg over big M mu s minus little m mu k times g. And anything to simplify here, I could factor out at mg over mu s, and I get 1 plus m over big M minus m mu kg. Okay. All right, so just kind of a lot of free body diagram, not like too hard, but definitely a little involved on the algebra to solve for that kind of thing. Yeah. Alright, let me see if there's another problem that I thought might have been interesting to look at, but probably not. Not at this time.